Okay, let's start. Um, so welcome everyone to this research seminar of the Best of Water Systems Research Seminar Series of the Center for Water Informatics and Technology at LUMS. My name is Talha Manzoor, and I'm an assistant professor at the center. And this is the fourth talk in this series, and um, so if you're attending this series for the first time, so this series is meant to celebrate distinguished works in water systems research, and today's talk in particular is about something that is very new and upcoming, especially in the hydrological sciences. And before I introduce the speaker, um, I, I'll ask Dr. Abu Bakr, the director of the center, to say a few words before I hand it over to the speaker. So,
Okay,
Dr. Abu Bakr.
right. So thank you, Talha. Assalamu alaikum and good evening and good morning to everyone around the world who is seeing this seminar. So this is a particularly exciting seminar for us in this series. I welcome Dr. Nering to the center, although this is happening virtually, but hopefully we'll have you here one day. The theme of this particular seminar is very close to our heart. So we are a center for water informatics or hydroinformatics, and our many of us are electrical engineers and computer scientists, and much of our training has been around, our work has been around this interplay between data and models. So at one time we were thinking that, well, if you have very little data available in ungauged basins like the Indus, so you have to do a lot of modeling. So you need to do a lot of physics, so to speak. But then with the advent of data technologies, we have been doing a lot of work in sensor networks. There is a lot of remote sensing data that's becoming available. So increasingly, we were sort of getting interested in marrying data with model with very sort of traditional data assimilation techniques of the Kalman filtering type. And that was our bread and butter for some time. But now we are moving towards this idea of a data deluge where we have so much data to look at, even for ungauged basins, especially powered by remote sensing, sensor network, citizen science, all of these developments. And really, the question is that do we need physics anymore? And this is where we, who are not trained as hydrologists, we are looking towards experts in the field to basically tell us, well, what is going on in their respective domains and disciplines. The whole field of machine learning, learning from data, that has taken almost every field by the storm. And what we are mostly interested in is same old idea. You have these hydrological laws at the catchment scale. How do they actually scale up or down as we move up or down? Are those still valid? And these new techniques, how are they useful in looking at this scaling issue? And also, I mean, looking forward, especially for basins like ours, like the Indus Basin, we have a very special situation here for ungauged basins, as I keep saying. What is the prospect of these technologies? What kind of transformation do we hope to see with the advent of these machine learning kind of tools? So that is what I'm looking for in this seminar. Some interplay of data and physics, data and models, and see what both can do together. So once again, welcome to everyone and welcome to Dr. Nering, and we hope to enjoy this talk and learn from you immensely. Thank you.
Okay, so thank you, Dr. Abu Bakr, and so it's an honor to introduce Dr. Gray Nearing, who is an assistant professor of environmental data science at the University of California, Davis, and a visiting researcher at Google Research. He was previously a member of hydrology modeling teams at NASA and the US National Center for Atmospheric Research. And Dr. Nearing's research is focused primarily on machine learning in hydrology and land surface modeling. So we'll hear more about him about this from him in a moment. So before I formally hand over to Dr. Gray, I'll just some logistics for the talk. So if there is any question on behalf of who are attending, there will be a short Q&A session at the end. And if you can use the Q&A button that you may see in your Zoom control panel. So at any point, you can just type in your question, and at the end, we will read them out and ask the speaker to respond. And in case you have to in case you need it, Dr. Gray has also very kindly agreed to the posting of the recording online as well. So it will be online on our website. So Dr. Gray, welcome once again, and I look forward to your talk, and please take it from here.
Thanks. Yeah, it's really an honor to be here. Thanks for inviting me. So I have a lot to say, and I think I'll just get started. I'm going to say one thing, though. After hearing what Prabhakar's introduction here, I think I'm going to do something a little bit risky and change up my focus a little bit. So at one point, I'm going to sort of speed through some slides at the beginning that I was planning on spending a little more time on, and then at one point, I'm going to stop the slideshow, unhide some slides that I had put in the background, and spend a little bit more time on the physics plus machine learning than I had maybe planned, just given what we just heard about the interests of the center. So bear with me when through that process. I think it'll be more in line with what you're interested in if we do it that way. So just to give a very quick overview. By the way, can you see my mouse?
Not yet.
You cannot see my mouse. Okay. Okay, so I won't use that. So, okay, so the basic challenge, the place we're going to start this story is prediction in ungauged basins. This is sort of a revisionist history. We didn't really start this project because of the ungauged basins problem, but it's a good way to frame sort of our early work in this space. Basically, if you don't know, the International Association of Hydrological Sciences back in 2002 decided that prediction in ungauged basins was going to be the decadal challenge for the association, and in 2003 to 2012, and in 2012 they published this review of the work that had happened during this decade of community focus on the PUB problem, prediction in ungauged basins. And sort of the review in 2012 was that pretty much nothing had happened. If you want to sort of state it bluntly, the success in improving models had sort of not infiltrated from improved predictions in gauged basins down to improved predictions in ungauged basins. Other things came out of this effort, like a sort of community engagement, community homogeneity, interdisciplinary research, but in terms of actually tackling the problem of prediction in ungauged basins, the community hadn't made any progress in 10 years. And really, to be perfectly honest, that was sort of true up through the present, up to a few years ago. We were doing a little bit better at assimilating remote sensing data of water level in big streams, but it's still in little streams, especially those headwater basins where flash floods were a problem. Our models are not doing any better than they were in 2012. Okay, just as a general rule. Okay, so what we did is we took a bunch of data from around the United States. So this CAMELS data set was curated by NCAR, the National Center for Atmospheric Research. It's a bunch of data related to different catchment characteristics. So these are 530, what you see the dots on each map are 531 watersheds within the United States that are gauged by the US Geological Survey. So we have long, at least 30 years of streamflow record in each of these basins. And we have pretty good estimates of precipitation, temperature, and humidity, as well as estimates of basin area, vegetation cover, geology, pedology, soils, sort of the basic things that hydrologists like to know. And we took this data set and we ran it through a very, very simple deep learning model, just a standard off-the-shelf long short-term memory network. I think I'll probably go through this. I'm sorry, I don't really know the background of most people here, so this is probably redundant for a lot of people. But basically, the long short-term memory network is a recurrent neural network. It has, and we like it especially for this problem versus other types of time series neural networks because it has a cell state. And when you build a dynamical systems model, so like a traditional model of a hydrological system, it's usually a PDE-based model. Most hydrology models are PDE-based models, or at least they're dynamical systems models, meaning they have a state that is updated through time. And the LSTM also has a state that's updated through time. That's this C. So C comes in at t-1. It's modified through a series of processes that are governed by various gates. Gates are neural networks, and it goes out, and we have a new cell state at time t, which feeds into the next time step. The outputs of the model, the HT up at the top of the screen, those are aggregated into our estimate of streamflow. So there's a little network up here that aggregates the outputs of the LSTM into an estimate of streamflow that's compared to observations through a loss function. And we have some inputs. These are the static catchment attributes related to soil, ecology, climate, catchment area, topography, and geology. The basic things that catchment descriptors, as well as the times. So those are the same at every time step because we assume those things don't change, except for a few experiments we ran where we looked at changing catchment attributes. But mostly those things don't change. And then there's some dynamic inputs. These are things like meteorological data, things like precipitation, temperature, radiation, and humidity. And then, so we have the cells that go in, and we have the some transformation of the cells called hidden states. And the hidden states are concatenated with the inputs at every time step, and those are fed into little things called gates, and the gates modify the cell states. And I don't want to get into the difference between the forget gate, the input gate, and the output gate. They're just ways to feed information from the previous time step and from the inputs into the cell states, and they do things like multiply. The forget gate multiplies by a number between 0 and 1, which means it always makes the cell state smaller. And if you make the value of the cell state smaller, then what you're doing is you're basically attenuating information from the past. Then you add information, you add to the cell state. So this can be positive or negative numbers. The tanh gate can be negative or positive, multiplied by a sigmoid is a number between negative 1 and 1, and you add that to the cell state. So this can add information to the cell state, and then the cell state goes on, and there's some nonlinear relationship between the cell state and the outputs. That's basically how this thing works. So this is a very cartoonish description of our experimental design, but really our experiments are just absolutely simple. There's nothing fancy going on here. We feed static attributes into an LSTM, we feed dynamic attributes into an LSTM, and we get the outputs. We use something like different experiments, 9 or 15 years of training data from 531 basins. And we always train, as I'll show in the next slide, we always train one model for all of the data. So unlike traditional hydrology models, where the best possible model that you can build, and this is true for every traditional hydrology model that I'm personally aware of, the best model that you can build is when you take a model and you apply it to a catchment that you have really good data for, long data records, really good descriptors of catchment attributes, and you calibrate that model for that particular basin. That's the way that traditional hydrology modelers work. They calibrate one model for one basin, and that's the best. That gives the best possible predictions. It's not the way that works with deep learning. With deep learning, the best possible predictions that you can make are when you take all of the data that you have and you throw them all into the training set for a single model. And so this is sort of an illustration of how that works with LSTMs. Basically, the dotted line here is we did hyperparameter tuning, not just training, but hyperparameter tuning separately for each individual basin, came up with different models, different training for every individual basin, just training a model for one basin at a time. So this really is just a huge amount of compute power that went into creating this dashed line here, hyperparameter tuning and training per basin. And then this solid line here is what happens when we throw all of the data into one model, hypertune that single model. And so this is a much smaller amount of computational effort, and it does much better. So If you're a computer scientist or if your background's in machine learning, this is not surprising to you at all because more data usually means better predictions. But if you're a hydrologist, this is complete fundamental change in how hydrological modeling works. Okay, and so what's happening here? Why is it the case that we want data from a whole bunch of different diverse basins in our training data set, when the problem in traditional hydrology is that if you put a whole bunch of different data, that in hydrology, this model here on the right, by the way, just so that we know how to read this plot, NSE is Nash-Sutcliffe efficiency. I'm going to use the Nse metric as a model evaluation metric for most of the rest of this talk. NSE is just an R squared value, so whenever you see NSE, just think R squared. It's just the fraction of explained variance. You want that number to be higher. This is the cumulative density function over the 531 basins, so the fraction of basins with an R squared value less than a particular amount. So what you want, a better model means this curve is further to the right, closer to 1. So better models are further to the right. Okay, so this model where we train or calibrate with all data from all the basins in hydrology, the name for this is regionalized modeling. This is regionalized modeling means calibrating a model to a region or a bunch of basins, and almost always that does worse than individual basin calibration. So why is it different in machine learning? The answer is really just because more data is better, and there's a paper by Martin Gausch and Julian May up at University of Waterloo that shows that. But if you want to actually see what's going on in the model, how the model uses that extra information from new data, we did a little bit of experiment to show that. We took the input gate of the Lstm and we froze it. So all the Lstm works just as normal, except the input gate only takes the static catchment attributes as inputs. It doesn't take any of the dynamic data. And what this does is it sort of freezes the input channel to the states. So when we pass new, again, the forget gate only sort of attenuates information. It doesn't add new information, but the input gate adds new information. And so what we do is we only allow channels from the inputs through this TANH layer. We only allow information to move through this TANH layer into the cell states of the Lstm. By multiplying with a sigmoid. Sigmoid is a number between activation function with a number between 0 and 1, so it sort of opens and closes channels of information. And we make the sigmoid gate only react to static catchment attributes. So what we're doing here is we're forcing the sigmoid gate to learn a representation of basin similarity. And this is what that representation of basin similarity looks like. So here's our 531 basins on the x-axis here, and on the y-axis are the input activations, again, responding only to the static catchment attributes, and there are 256 cell states, so there are 256 input activations. And what you see here is this is the model's learned representation of basin similarity. Of course, to a human, this looks very much close to nothing, but it is the best representation of basin similarity that exists in the hydrological science community right now. And my argument always is when a traditional hydrologist looks at this and says, oh, that means nothing to me, what I usually like to say, which happens every time I present this plot, what I usually like to say is it really doesn't matter if it means something to you because it means something to the model. And if we had been able to solve this problem in a way that was interpretable to humans, that would be excellent. But the reality is that we haven't. After 30 or 50 years of trying to do it in hydrology, we haven't been able to do that. And so that we get practical answers that look like this. One interesting thing you can see here are these sort of horizontal bands. So you see that some basins look similar to others. And what's happening here, these basins are grouped by geographical location. They're grouped by US Geological Survey Basin ID. And so what's happening here is that the model is learning that basins that are close together have patterns of information use that are similar. So there's nothing about geographical location, no latitude, longitude, no location information is fed into the model, but it kind of learns that basins with similar climate and vegetation and whatnot behave similarly. Okay, so we can kind of break this down. I want to skip this mostly because I want to talk a little bit more about physics-informed learning, but we can do sort of a clustering analysis on this to try to make sense of it in a more human-readable format. I'll just point out that if we do a clustering analysis on this to try to see what what are the major sort of first order clusters of basins that come out of this activation layer, this sort of hidden layer in the model. We get 4 or 5 clusters, and those clusters correlate most strongly with vegetation related information. Again, if you want to hear more about this, I'll talk about it, but I want to sort of speed through these slides faster than I was expecting. Okay, so here's our first benchmarking result. The way this benchmarking happened is there's no benchmarking in hydrology. So unlike a lot of different science communities, the hydrology community doesn't maintain a community standard benchmark. So there's nowhere on the web that you can go and look up which hydrology models are currently doing better on standard data sets. So every benchmarking study in hydrology has to do that themselves. And the danger there is that if you have a new model and you want to benchmark it or see how well it's doing against other models, you have to be the one to run those other models yourself. And that's dangerous because it takes a lot of skill to run a hydrology model. And so what we did in this case is we didn't run our benchmark models ourselves. We went out to the community and we asked other modeling groups to sort of contribute their modeling, calibrate their models and contribute their modeling results to a benchmarking study over the Camels basins. So this is a pretty well-known data set. So several groups were willing to do that for us. We have the SAXMA, which is the NOAA model in the United States, variable infiltration capacity model out of the University of Washington, a couple of European models, and then FUSE is sort of a model that sort of historically came from a collaboration out of Australia, Canada, and Europe. A lot of people own this model. And then there's an Lstm, which is just our standard implementation of an Lstm, and we're going to forget about the MC-Lstm until later. So the Lstm sort of did a benchmarking wise there was sort of a step change in performance compared to the traditional hydrology models. And this is a pretty good representation of existing models. So again, these models were calibrated by research groups that have at least 15 years of experience with most of these models. And they contributed their data on this data set to this project. And so these were not run by us. And then we built the Lstm. And so you can see that there's some, what this is really telling us is that there's more information in the observation data that hydrologists have available than we are able to extract by using traditional methods. Okay, so this is really the answer to the question we started with. How well are we doing in ungauged basins? We saw earlier that the model has this ability to learn a representation of basin similarity. That's what allows it to move information from one basin to another. We saw an effect of that earlier, where a model trained on data from multiple basins does better than a model trained on an individual basin. That means it's learning something generalizable about hydrologic behavior. So here what we did is we did a k-fold cross-validation study where we left some of the basins out randomly and then trained on 90% of the basins. We did a 10-fold cross-validation. And we found that the results from that are this yellow line with stars. So here we're comparing against the 2 NOAA models. These are the 2 operational models in the United States. SAXMA is the Sacramento Soil Moisture Accounting Model. It's underneath the CHIPS. It's underneath our major flood forecasting system in the United States. And this is the U.S. National Water Model. So this is the distributed, hyper-resolution, process-based hydrology model that's run by the U.S. government, the NOAA in particular, and Sacramento is also run by NOAA. Sacramento is what actually gives us our flood forecasts, and the U.S. National Water Model does some other more research-like stuff in the background. But there are 2 operational models. So the Lstm is our best predictions at these basins if they were gauged, and the line with stars is the ungauged basin CDF. And what you can see is that in the range of above about R² of 0.6, we do better in ungauged basins than the Sacramento model, the operational US model in gauged basins. So just to be clear, the Sacramento model is not ungauged. The Sacramento model that we're comparing against here is calibrated separately for each individual basin, and it was calibrated by INCAR, so not by our group, but by the group that really runs this model. The U.S. National Water Model is also calibrated by INCAR, which is the group that developed that model. So these two models are calibrated per basin. This yellow model is the regionalized Lstm, and the yellow star is prediction in ungauged basins. So what we're learning is not only is there more information and observation data about stream flow than traditional hydrology models are able to extract, but there's so much more information and data that we can do prediction in ungauged basins with accuracies that are generally, at least on average, better than traditional hydrology models can do in gauged basins. That's really the takeaway here. So I have this whole spiel about what this says about the state of hydrological sciences and about how physical hydrologists sort of do their work, and I think it's a pretty negative reflection on the state of hydrological sciences. But the point is that there's a lot of potential here to do sort of the real world jobs that we're trying to do much better than we have in the past. Okay, so we can do a couple other cool things. We can do uncertainty estimation. Really going to go fast here now. But basically, we do uncertainty estimation by adding mixture density layers to the output of the neural network of the Lstm. So instead of predicting stream flow directly, we predict the parameters of a mixture probability density function through a mixture density over a probability density function over stream flow. Okay, so just say it again. Instead of predicting stream flow exactly, we predict a probability density function over stream flow, and we calibrate using the log likelihood loss as a loss function. We can use Gaussians, or we can use other types of distributions. We tried a few distributions, and the one that works really well for this case is a heavy tail distribution. So we used asymmetric Laplacians. Two things came out of this. One is that we actually got better deterministic results by using a probabilistic layer at the output of the neural network, and that's because it allowed for heteroscedasticity in the loss function. But we also got really accurate, aggregated at an aggregated level, very accurate, statistically accurate predictions of uncertainty. So here's our sort of benchmark of a few different methods for quantifying uncertainty. And one of these, this is a countable mixture of asymmetric Laplacian distributions in the output of the in our kernel density function. Sort of gives aggregated over the 531 basins, all of the test period, gives sort of a statistically perfect quantile representation of uncertainty. We can go more into that if we want, but the point is it's possible to do it. You mentioned data assimilation in the introduction. We can do data assimilation with LSTMs because they have a state space. So any normal type of data assimilation applies directly to LSTMs, Kalman filters, particle filters, Markov chain Monte Carlo filters. Any of these things are just applies just in an absolutely straightforward way. It's just you do it exactly like you would a normal model. Variational data assimilation is especially interesting in the in a deep learning context because you can leverage the tensor network that the models are built on. So these deep learning models require backpropagation for training. Backpropagation are just adjoints. So you don't need to write an adjoint function. You don't need to use an automatic differentiator. Actually, you do. It's built into the tensor, the machine learning library by itself. So we leverage the automatic gradient capabilities of these tensor networks that the machine learning models are built on to do variational data assimilation. So I'm going to just assume, since it was mentioned in the introduction, that everybody understands what data assimilation is, and just point out that we can apply data assimilation straightforward to these models. The one that we're specifically going to test here, and the results I'm about to show, is variational data assimilation, where we use the tensor network itself to do the updating. So after we've trained the model, we freeze the weights and the biases of the model, just like in a normal machine learning situation. We use that model to make predictions going forward into the future. But during inference, so after the weights and biases of the model are trained and frozen, we're still going to leverage the gradient chain, the backpropagation gradient chain in the tensor network to update the cell states of the model. So we're going to point the backpropagation now. We're in inference mode. We're going to point the backpropagation not at the weights and the biases of the model, but we're going to point the backpropagation at the cell states of the model. And we're going to use that. There's a one-to-one sort of correspondence with traditional variational data assimilation. We're going to use that to assimilate yesterday's stream flow observations. So we're going to, here, you could assimilate any type of data you wanted. You can assimilate remote sensing data, map data, soil moisture data. You can assimilate data. We're using this operationally at one of the companies I used to work for to assimilate in situ measurement data that only exists in some of the catchments. So if you have some catchments with more data than other catchments, you still want to train the model using all the data together. But now you have some data that you couldn't use for training. Well, you can use that through backpropagation. So you, like, if we have a snow station in a particular catchment, we'll actually train the model to predict both stream flow and snow at that catchment, and then we'll use backpropagation to ingest that snow data into the model. And that allows us to do training on all the, or that allows us to use all the data we have to make prediction, while still allowing us to train on only using the data that's consistent across all basins. So there's several uses for this, but for right now, we're just going to use it to assimilate the observation from the previous time step. So stream flow here from the previous time step. But there's an easier way to use stream flow from a previous time step, or almost any type of input data in a deep learning situation. If we were simulating remote sensing data or of any type, we could just feed it into the inputs, right? That's an easier way to do this. And so if we're feeding in yesterday's observation data into the inputs, that would be a form of autoregression. This is common. In fact, until 2019, almost all, I believe all except for one or two of the machine learning applications in hydrology used autoregression. Okay, so we're just going to compare these two methods. We can do data assimilation with the tensor network versus autoregression, which is more natural in a machine learning context. And we can see that in this particular case, autoregression works just as well as data assimilation, actually slightly better. And this is, by the way, these results, we really wanted data assimilation to work. So the story here is we figured out we could use backpropagation to do data assimilation. We were super excited because I spent the early part of my career building data assimilation systems for hydrology models, and it takes months or years to develop a good data assimilation system. Here we can develop a data assimilation system on a deep learning model in a matter of hours. It's literally like 6 lines of code, and then you do some hyperparameter tuning. So we really wanted this to work. This was what we wanted to publish, but we couldn't ever beat autoregression, which is, it turns out to be a much simpler way to use observation data. And so the lesson that we learned here is that simpler is better. And so what I'm saying is, while it's possible to do data assimilation, you don't have to. You can, there's other alternatives that don't exist in traditional modeling. We took this to NOAA in the United States and said, well, why don't you guys use this for flood forecasting? NOAA funded us to do some work to look at that possibility. And one of the responses we got was, well, you can't do, you're doing daily forecasting. Everything we've been doing is at the daily timescale, but for flood forecasting, we need hourly. So we did an experiment where we created hourly predictions. And the NOAA model here is in red. This is daily predictions in solid red and hourly predictions in the dotted line. And basically what happens is the NOAA models can do hourly predictions, but they're less accurate than daily predictions. And this is, of course, completely expected. Whenever you aggregate over either time or space, you gain some statistical accuracy. This is true for every hydrology model that I'm aware of. When you aggregate results over time and or space, you usually get better predictions, and that's true for the US National Water Model. But it's not true for our deep learning model. We trained a daily model and an hourly model. I'll explain in just a minute the difference, and we did not lose accuracy. So our hourly predictions are sort of equally as accurate as our daily predictions. At Google, we're doing the hourly predictions now for our operational models. Basically, the strategy is, the problem with hourly predictions in a deep learning setting, especially with recurrent neural networks like an Lstm, is that hydrological memory is a lot of hours. So if you think about the sort of antecedent conditions for a particular flow event or flood event, how many hours of historical precipitation you would need to fully understand those antecedent conditions. Even if we don't account for groundwater, you're looking at, in some catchments, it could be up to 180 days to really have the full hydrological memory. And that's a lot of hours, and to do sequence prediction in Lstm. That forget gate introduces numerical noise, so you can't really have sequences of 17,000, or even 8,000 hours. You're just not getting information that far back in the chain. So what we did is we had a daily model, Lstm model, and then at one point when we wanted to start making hourly predictions, we had the daily model roll back to account for hydrological memory, and then we took the cell states and the hidden states of the LSTM, and we used those to initialize the cell states and the hidden states of an hourly model. And then we run the hourly model alongside the daily model, and we have a regularization in the loss function so that every 24 hourly blocks, the sum of the stream flow from the 24 hourly blocks, or the average, depending on the units you're using, should equal to the prediction made by the daily block. So we add that sort of regularization constraint in the loss function, and that's how we're able to get hourly predictions that consider the full sort of hydrological memory and also run in finite time. One common criticism of machine learning that you hear everywhere is that it doesn't work for out of sample or extreme events. It's kind of funny. We used to hear this all the time when we presented this work at conferences from hydrologists, and I went and looked, and there aren't actually any papers that show this. There are, to be fair, there are some using very, very simple data-driven modeling strategies, very, very simple modeling strategies from 10 or 20 years ago that shows some degradation in predictions of out-of-sample events. But this was such a common criticism of machine learning that we heard from everyone the first few years we presented this, and it was sort of, it's kind of funny, it was sort of taken as truth, but we couldn't find any data to sort of, any experiments that really demonstrated this in this particular domain. And so we did some experiments ourselves. We took the return, we looked at the return period of all of the data in the CAMELS data set, the 531 basins that we've been looking at. We found the return period of every basin year, every year of data from every basin in the data set. We divided our training sample up, so we took all the years worth of data with return periods of less than 5 years, less than 1 to 5 years. So there were 5,969 water years worth of data where the return period for that particular basin was between 1 and 5 years. And then we tested on return periods in all of these categories: 5 to 25 years, 25 to 50 years, 50 to 100 years, and then 100 years plus. So these are the number of water years in the CAMELS data set, basin-specific water years with these particular return periods. And of course, we did return period calculations separately for each basin. And what we're looking at here is the blue box. Please ignore the orange one, but the blue box compared to the green and the gray box. And so the blue box is sort of how the prediction of peak flow events. So this is the absolute percent bias of peak flow in a given water year. So how the average absolute percent bias of peak flow changes as we move out of sample. So from 1 to 5 years all the way up to 100-year return period events. And we do lose some accuracy. You can see the mean, or the mean of the blue box, which is the LSTM, does increase. Higher scores are worse here, but it doesn't increase as fast as the traditional hydrology model. So the sort of conceptual model, this is the Sacramento model, the conceptual model loses accuracy much faster than the machine learning model, even for out of sample events. The gray box is the national water model. So that's more of a physically based model than a conceptual model. And it loses accuracy faster than the LSTM does. But the reason this is sort of grayed out is because the national water model was not calibrated by restricting only to low return period events. So the national water model here was calibrated by NCAR, and it was calibrated sort of on a whole time slice. So the calibration period for this, for the national water model, included just randomly events from all of these different return period categories. We weren't able to calibrate it on our own, but even given that we're doing a more strict split calibration validation split here, we still lost less accuracy than the physically based model that was calibrated even differently. So yeah, okay, so yeah, let's start here. So one of the academic responses to this work, so I think you guys all probably know that there's sort of a faction in hydrological research that doesn't like data-driven modeling, thinks that the hydrological science is really about understanding how water flows through the environment. I disagree with that. I think our purpose here is primarily to provide information to society, and that understanding the physical hydrological processes is one tool that we have available for us to do that. But Keith, I guess as most people here, anyone that's in the hydrology community knows Keith Bevan and knows that he's a physical hydrologist. And so his response to this work was that it wasn't surprising that the machine learning models are doing well because of errors in the data. So he said, If it's the case that there's sort of consistent biases or consistent errors in the data, that's the precipitation and or streamflow data, then a model that's not constrained by mass balance could learn to accommodate for these errors. And in fact, that is the case in the CAMELS data set. So these are two different precipitation products, DayMet and NLDAS. And this is a way to measure bias in the data products. So this is running these precipitation products through the Sacramento model. So a conceptual model, again, that's calibrated per basin, and then looking at the percent error of the long-term mass balance in the streamflow. So over 10 years, the cumulative output from the streamflow, what's the percent bias on a model that's calibrated to that particular basin? It's just a quick way of looking for potential biases in the data. And what we can see is that in the DayMet data, which is one of the precipitation products, there seems to be strong biases, overestimation biases in the DayMet data in the eastern half of the United States, and that's not true for the NLDAS. So the NLDAS is another precipitation product that doesn't have this particular geographical bias. So we have an experiment to test Keith's hypothesis. Keith's hypothesis, again, is that one of the reasons that machine learning does well is that it's able to sort of learn systematic errors in the data. So we have this sort of, and specifically he's talking about errors that might cause problems when used in a model that enforces a mass balance. We also have a neural network that's constrained to conserve mass. So we've been working on this since about 2018. This is a version of the Lstm that we developed that sort of obeys mass balance principles. This is something that we could spend a whole lecture on going through, so I'm not going to. I'm just going to tell you that the trick to enforce mass balance in an Lstm is basically, the way that we did it is basically we turned all of the gates, the sort of the input gate, instead of a forget gate, we have a reshuffling gate. So instead of just forgetting mass or forgetting information in the cell states like you do in an Lstm, we actually move information around between cell states. So we have this reshuffling matrix that's multiplied, column-wise normalized and multiplied by the cell states. Then we have the output gate like a traditional Lstm. And the trick that we played is that instead of using regular sigmoid activation functions for the gates, we used normalized activation functions. So all we did is we added a normalization layer to each of the gates in an Lstm, and we multiplied the normalized outputs from those normalized sigmoid gates by some quantity that we want to conserve. What that means is that the outputs from all the gates that go into the cell states are multiplied by some quantity that we overall want to conserve. And here this is precipitation, so we want to conserve the total water going into the system. So we conserve precipitation, we multiply it by these normalized sigmoid gates. So the sum of all the information transfers from inputs to cell states always sums up to the total amount of precipitation. And then we can reshuffle column-wise normalized so we don't lose or gain any mass. And then the output gate, we play the same trick so that the amount of information that comes out of the cell states into the prediction of streamflow is always less than the total amount of the total value of the cell states aggregated. So the cell states actually keep track of mass, but we still retain sort of the neural network abilities to learn these fluxes into and out of the system. That's the trick we're going to play. And in fact, what we see is when we train, these are cumulative density functions of long-term mass balance errors in the model. Here, 0 is better, so we want the curves to be as far to the left as possible. And what we see is the Lstm and the mass-conserving Lstm. The Lstm is sort of able to learn almost the same long-term mass balance as the MC Lstm. That's the real story here. When we use the biased precipitation product, the Sacramento model calibrated separately using this data product, calibrated separately to every basin, is not able to compensate for that bias in the data. That's sort of the lesson here. Even though it's calibrated separately to each basin and the bias is different in each basin, it's not able to account for that bias. When we use the unbiased or the less biased precipitation product, the traditional models, the Sacramento model, and here we can use the National Water Model because we have a version of that uses NLDAS. We can see that the total mass bias is less, but it's still not as good as what's learned from the both the Lstm and the mass-conserving Lstm. Okay, but we do lose skill. So even though the Lstm is able to sort of learn the same long-term mass balances as a version of the Lstm that's constrained specifically to conserve mass, the constrained model isn't able to pick up all of the variation in the data, and so we lose some correlation. So the sort of correlation score goes down when we constrain the model to conserve mass, and also the ability to predict peak flows, extreme events that are not included in the training data set, also that skill is also reduced. So the mass constrained neural network does worse than the unconstrained neural network. And really what that was surprising to us, because we really thought that would be these out of sample extreme events where having a mass balance would help, but that's not the case. So yeah, and so what's happening here is that there's some probabilistic consistent biases in the input versus output data that we're able to learn with a neural network that's flexible enough to be able to learn that the total mass inputs don't always match the total mass outputs. Okay, so that's sort of the major story of our journey with LSTMs. There's more parts of it, but that's sort of it. What I really want to say a few words on at the end here is about combining physics with machine learning. And we're out of time, unfortunately. But so I'm going to go really fast through here. But basically, there's a few ways that people have come up with to integrate physics and machine learning. One of them is post-processing, which is using the outputs of a physical model as inputs to a machine learning model. That's really boring, but people do that. We had some slides earlier that I skipped that sort of showed that, and in our case, it doesn't work. We're not able to take the outputs of, for example, the US National Water Model. We're able to get those outputs up to the scale of the deep learning model, but not above it. You can use regularized loss functions. I personally have not worked with that at all. That's the most common way to include physics in machine learning. We can use architectural constraints. So I gave an example of that with the mass balance constraint LSTM. You can put machine learning into physics models, and I am going to say a few words about that. And then you can also actually encode physics as layers in the tensor network so that you can differentiate through actual physical modeling components. And you can build models by sort of treating physics descriptions of physical processes as layers in a tensor network. And here's a really interesting reference that shows that. So I won't talk about that more. I'm going to talk just a little bit more, very, very quickly, about putting machine learning into physical models. Excuse me one second. Basically, the strategy that we've tried to do that is we take a model that's based on a differential equation. So we have dx dt. This is some system of PDEs is equal to some function of states, boundary conditions, and parameters. So we have some sort of conceptual model that's framed as a partial differential equation. Dx dt is equal to f of x. And then we can add some correction terms to that. We can add a structure. We can add a machine learning component to the PDE before we solve the PDE. So if we learn some term that acts on the current state, some boundary conditions, and some parameters, we can then include that in the PDE, and then we can send this whole thing to the PDE solver, the thing that we would normally use to solve the PDE in our hydrology model. And we can train this machine learning model here to add information from observations to sort of correct the errors in a dynamical sense of the machine learning model. And then we can also add a learned stochastic term if we want to do probabilistic prediction. That works. So we've done that with Streamflow models. This is a paper published in 2015 where we did that with a very simple Streamflow model. And what we found was that it works much better than parameter estimation, and it actually it basically has the same skill as data assimilation. But what it does is it allows us to keep that skill. So when you assimilate Streamflow data into the model through Kalman filtering in this case, then you get improved predictions in time periods that are close to when you have observation data available to assimilate. But we were able, by assimilating that data, we used data assimilation to learn that machine learning term in the PDE. And then once that term is learned, we unrolled that for like 3 years after our last Streamflow observation, and we retained most of the information that we were able to learn through data assimilation. We retain that in inference mode. So we do data assimilation, it corrects the trajectory of the model, but then we use that corrected trajectory to learn this other term in the PDE solution, and then we roll that out for a long forecast period, so way beyond the hydrological memory of the system, and we see that we continue to see the benefits of data assimilation way out into the future. So So that's sort of how we approached this physics-informed machine learning. But I will say that even though that was successful, we were never able to match the performance of just a pure machine learning model. So this model is great. We built this. It works much better than the machine learning model itself. We use data assimilation to train it. But if you just take out this F term, if you just take out the original conceptual model and only use the machine learning model, it's still better. That's not shown on this slide, but the lesson is that it was still better to use just pure machine learning than this physics-informed approach. Okay, 3 more examples from the literature, 1 slide each. This is from Pierre Gentine's group at Columbia. He used a physics-constrained neural network to predict latent heat fluxes. He found the same thing. Pure machine learning wins over the hybrid physics machine learning model. This is an example from University of Washington, Bart Neeson's group and Andrew Bennett. Basically, they added a machine learning component to an existing land surface model to predict evaporation. So the land surface model acted as it normally does, but the evaporation equation, which would be something like Penman-Monteith usually, or one of the other evaporation equations, they replaced it with a neural network that was trained in a pretty robust way. And they found that this did better than this hybrid model did better at predicting latent and sensible heat fluxes than either the neural network by itself, which is the red model. The coupled model is the orange. The neural network by itself is the red model. So pure machine learning is the red model. And the process-based model is the blue model. So their hybrid physics plus machine learning model did better at both predicting sensible and latent heat fluxes than a pure neural network. But they made a mistake. What they did is that they trained their pure machine learning model had no memory. It only took instantaneous meteorology to predict instantaneous latent heat flux with no hydrological memory at all, while their physics hybrid model had memory in the form of a soil moisture state. And so the hybrid model, the orange model here, had a distinct advantage. It didn't get the same, it got more input data than the red model. And so I recently corrected that error and found that pure machine learning can beat their, so this is exactly their same results, but sensible and latent heat flux. And if you use a pure machine learning model with memory, you can do better than their hybrid model. And so my conclusions, the thing that I'm really trying to stress in the community right now are the following. One is that our observation data contains a lot of information, much more information than even our best hydrology models are able to extract. Our job, if we want to make better predictions, we can do better than we're currently doing. The data has more information than we're currently using. The reason, yeah, that's not important. So I'm aware of, there are a ton of studies published in hydrology literature that claim to have found value in hybrid machine learning plus physics-based modeling. I will say that I've read, I think, all of those papers. We have a real problem in hydrology of people that don't understand what they're doing, publishing machine learning studies. I've not found a single paper that shows this in a way that doesn't make extremely basic mistakes. So Andrew Bennett's paper is one example of that, but there are many, many more. Xiaopeng Shen has published some ridiculously bad papers that claim to have shown this. So be careful when you see people making this claim. My personal opinion is that there aren't any papers that show this in traditional streamflow modeling or land surface modeling yet. I'm sorry to be so blunt, but there's a lot of really bad studies out there right now. So what I'm encouraging the community to do is this hybrid modeling strategy is interesting. This is what most of the machine learning based hydrological research is working on, that I'm aware of, is working on right now, is this physics informed machine learning. And my suggestion, what I would like to see more of than what I'm seeing currently is first finding a specific deficiency in the data that needs to be corrected, and then looking for ways to correct that with theory. What's happening now is people are taking the models they're used to, they're taking these new and exciting machine learning models, they're combining them together. People are really excited about that because the machine learning models are doing really well, but people also don't like to give up what they're familiar with. So the idea of combining these things is very attractive. Again, I will say that I haven't seen a convincing example of this yet. The papers that I reviewed are sort of the best papers that I've seen so far. There are others for sure, but what I haven't seen is someone go through and find a specific deficiency in the data or a specific deficiency in the machine learning model that needs to be corrected, and then go and ask the question, well, how do I correct that with the theory that I have available? That's an approach that I've seen taken in a lot of disciplines outside of hydrology, or at least outside of surface hydrology, land modeling, and streamflow. And I think that I think that would be a great way to go. All right, thanks for your time.
Okay, thank you so much for the very insightful talk. And indeed, the stuff that you have been able to do with purely data is mind-boggling. And I can imagine that this would be very difficult to digest, especially if, by the hydrologists who have spent, like decades and decades making these physical models. So, because we have less time, just let me very quickly read out the Q&A that we have. So starting from the shortest one first. So we have Dr. Malik Jahan, who is asking, is the data that you have presented in your studies, how is this work publicly available?
Yes, everything's publicly available, both the input data, which is not ours, it belongs to NCAR, and the output data. If you go read our papers, this is our first priority, is community science. There's all of our code, all of our data is available. More than that, we've made an effort to make sure that if you want to reproduce our studies, you can do that almost with no effort. So all you have to do is download the data. Our code is set up to be push buttons, so you should be able to reproduce our studies in no more than 3 commands at the command line. That's our goal, and I think we're there. So there's a couple of we've made our own extensions to the CAMELS data set, extended it from 2008 to 2014 for some studies we wanted to do with the National Water Model. Those extra CAMELS data, which are not hosted by NCAR, are available publicly on Kuashi server in Tufts University. And those extra data sets are also linked in our papers. I'm happy to provide if you want to email me, I'm happy to provide a roadmap of sort of all the data that is available.
Okay, so I have a question. So because you go outside of regionalized modeling, then so does this mean that we can potentially learn a model from basins in the US and apply that to some ungauged basin in Pakistan?
Yeah, that's a great question. So we don't know the answer to that, and that's actually one of the projects we're working on now. So we don't know the best way. So here's the way that I frame the question. This is literally what my research group is doing now. So we don't know if it's the case that if you want to build, let's say you want to build a global model, we don't know if it's the case that you want to train with all the data that you have available, if there's some limit to that phenomenon, or if you want to sort of group catchments either geographically or by hydrological characteristics in some way, and then train multiple models or train one model as a whole. We don't know that. So CAMELS now has been extended to Brazil, Argentina, UK, Australia, and Brazil, Chile, UK, Australia, and the United States. So there are 5 CAMELS data sets now. And so this provides us sort of a test bed that we can do these kinds of studies. So the 2 questions are, do we continue to train the same way, use all the data available, and then use that one model to predict everywhere? That's the first. Or do we try to cluster the basins ahead of time? And the hydrological instinct is to cluster the basins ahead of time and then make predictions with different models based on different regions. And the second question is, how much accuracy do we lose when we move from country to country? And it's probably not as simple as that. It probably has something to do with climate zones and hydrological characteristics, but we don't know the answer to that question yet. And then, of course, there's the third option, by the way, that makes this even more complicated, is transfer learning. So let's say you have a model you want to apply in Pakistan, and you have, I don't know, maybe 12, I'm just as a number, maybe like 12 gauges that you have available for training. 12 gauges, something like that, order of 10 gauges is not enough for training one of these models robustly. So, but maybe you could train a model with all of the global data and then use transfer learning to sort of tune it to the specific hydrological situation in a particular region. That's, if you want my guess, that's probably what's going to be the most successful.
Okay, thank you. So reading out the next question, can these machine learning models be trained using remote sensing data?
Yeah, they can. And so the way that you do that is you put the remote sensing data in some form into the inputs of the model. Okay, I also actually have a student working on this now. And the question that she's looking at is, let's say, so right now we're doing lumped catchment modeling. We're not doing any distributed modeling within a particular catchment. These are all lumped models. That's not completely true. The startup company that I worked for 4 or 5 years is doing distributed modeling with these LSTMs now. But for all the results I showed right now in this presentation are lumped models. So you take remote sensing imagery, pixel-based. Usually this imagery is pixel-based. And you have a question. Do you feed in the image itself into the inputs of the model, or do you take aggregate statistics over those images and feed it into the model? And right now, we're looking at vegetation data. We also should be looking at soil moisture data, but I haven't gotten to that yet. But with the vegetation data, we saw earlier that vegetation was one of the main characteristics that the model used to group basins in its sort of embedded representation of basin similarity. So we started with vegetation data. That's MODIS and Landsat data. And we're finding that the amount of complexity needed to add a series of convolutional layers in order to do image processing at the beginning of the model that would allow us to use these sort of spatially distributed, basically image-based representations of vegetation. We're finding that on average, that doesn't necessarily add as much value due to the extra complexity that's added as just doing feature engineering and taking something like the mean of the NDVI. We're actually getting on average better results just doing something like catchment mean NDVI and taking dynamic time series of vegetation. It's the vegetation dynamics that we see tend to matter more than the spatial distribution of vegetation. Now, if in 10 years looking back on this, what I would guess we would see, in the future is once these models are built out, once we have a real data-based, machine learning-based hydrological model that's fully distributed, meaning distributed within a catchment and also with a routing function that links catchments to catchments with some sort of routing, machine learning-based routing function. By the way, we're using graph convolutions as our routing function. I didn't talk about that either. Once we have that full model sort of built out and running globally, my guess is that we'll have much more opportunity to look at special cases where within catchment distribution of vegetation matters. But right now, on average, using the model setup that I just showed, what we're finding is that it's the time series vegetation dynamics that matter more than the spatial distribution.
Okay, thank you very much. So because we're out of time, maybe just let me hand over to Dr. Abu Bakr for any concluding remarks.
Thank you, Talha, and thank you, Greg. I mean, that was exactly what we were sort of hoping for. You kind of an expert opinion on, because we have also been reading papers, various approaches, and actually you gave a very candid opinion at the end of what kind of approaches actually are working and not working. This is a very new field for us. We are not even from this field, so to speak. I mean, we have colleagues here who are experts in machine learning, and we are still learning about these new techniques. But when we read papers on hydrology, which is not our subject, and also machine learning, which again is not our subject, so it's very important to get opinion from leading researchers like yourself on what is working and what is not working. I mean, I was especially intrigued by all these approaches where the physics was being added to the penalty functions. And what I saw in your talks was basically you're tweaking with the structure of the neural network directly. So I mean that's a very interesting kind of a comparison, and for us to learn quite a bit from. And so we'll follow some of the leads that you have given us. So thank you very much. I look forward to remaining in touch with you, and hopefully some of the work that you are doing, these ideas of transfer learning, whether they are in the form of actual data and models, or whether we are learning directly from you, I think this will be very useful going down in the future. Yeah.
I'd like to clarify one thing I said, just because I did give that candid opinion at the end. And given what you just said, I've spent zero time looking at these regularized loss functions for adding physical constraints. I did that. The reason that I made that choice was because that was the strategy that I've seen most often. And I figured that it would, since I saw quite a few people doing that, I thought it would be best to sort of leave that to others. Mm-hmm. So I haven't even kept up with the literature on that to be perfectly honest. So I want to make sure that I'm very clear that my opinion about the state of physics-informed learning, and I think I said this probably too briefly in the talk, doesn't extend to that particular type, regularized loss functions. And I do know, from what I see, just sort of subjectively, I haven't quantified anything, but that does seem to be the most popular way that people are doing this.
Fair enough. Fair enough. And like I said, I mean, we will keep looking at the literature both on that more popular side of things and the approaches that you are using. But once again, this is very fascinating. I mean, both approaches, they sound very fascinating, especially for novices like us who are really going into this field for now. Talha, over to you if you want to end this.
Okay, so Dr. Gray, thank you very much once again, and to all of the participants as well. Thank you for listening. The talk, the recording will be uploaded soon on our website, and you can also tune in from time to time to see about the other talks. We have an exciting lineup of speakers in the future as well. So remain in touch and take care. Allah Hafiz. Goodbye.